Imagine you're a young helmsman standing on the deck of a massive ship, and steering your vessel is nothing like driving a car. No roads, no signs, only your eyes and the horizon ahead. You turn the wheel to the right, and nothing happens. Only seconds later does the ship slowly begin to respond, only to swing too far off course. You twist the wheel back and now drift the other way. You wrestle with the wheel, and somehow the ship never seems to go exactly where you want it. But this isn't just a nuisance for sailors. For hundreds of years, this seemingly simple problem has plagued some of the greatest minds of physicists and mathematicians. Then, in 1922, a Russian-American engineer invented a mathematical equation so simple yet so important it's been used in all automatic systems: cars, ships, rockets, drones, and even the air conditioner and oven inside your own home. In fact, it works so naturally that every time you press the gas pedal or adjust the shower temperature, you've probably been using the same principle unknowingly. So what is this magical equation? It all starts with one simple question. How do you convert one value to another? At the beginning of the 20th century, when the modern industrial era began to gather steam, scientists increasingly wanted to pursue automation and systemization.
Hard labor, says Henry Ford, should not be for men, it should be for machines.
Manufacturing processes of the time, such as producing machine components or fine-tuning automobile engines for major companies like Ford, General Motors, Firestone, and Harley-Davidson, demanded greater precision than ever. And with that came the need to turn the tedious work of design and hard labor into numbers and mathematical equations, making production more robust and convenient. One of the growing interests of this is controllers. Everything around us, from an AC changing temperature, a car maintaining its speed, or a ship attempting to steer, they all need a system that can change an input from one value to another, automatically with minimal error. This is the foundation for control theory. It is a field of engineering that deals with dynamical systems and how to control the behavior to meet the needs of industries, like controlling water level or temperature. Automatic controllers have been invented as early as the 17th century. Then Christian Huygens invented a centrifugal governor to regulate the millstones in windmills. Some decades later, in 1788, inspired by this design, James Watt invented the conical governor to control the amount of steam in steam engines. This invention culminated the steam age in the 19th century and was quickly adopted in various steam engines, combustion engines, and some turbines. However, this centrifugal governor has a problem. If we increase the load of the engine, the speed decreases significantly, and with just enough disturbances, say a sudden gust or a sharp incline, regulating the speed properly becomes a difficult task. Because of this, in 1868, James Clerk Maxwell, a Scottish physicist, submitted a paper to the Royal Society of London named On Governors. In it, Maxwell systemized various types of governors with mathematical analyses to, quote, direct the attention of engineers and mathematicians. Although Maxwell's research later became famous and extremely important in modern control theory, back in the 1800s, it drew very little attention. At that time, most dynamical systems were about controlling temperature, pressure, water levels, and rotational speed. Engineers only cared about stability, not precision, so for them, the governor was good enough. But when the 20th century arrived, a major event occurred. World War I. And suddenly, the militaries of powerful nations like the US, Britain, and France required larger and more sophisticated guns, cannons, and warships for warfare. And with the invention of the underwater torpedo, a simple centrifugal governor suddenly became useless against all these giant machines. Engineers at that time instead turned to studying steam, hydraulic, and pneumatic control systems in order to improve the precision of control. And in 1922, the task of improving control precision fell to the Russian-American engineer Nicholas Minorsky when he was developing an automatic shift steer system for the US Navy. And out on the vast ocean with heavy naval ships, steering had to be highly precise to save fuel and ensure safety. At that time, however, the heavy load causing instability in the system still remained a problem. But then, what exactly is the problem with control systems? You might think that a control system is easy to set up to convert one value to another, say heating up water. You might think it's just about turning the temperature up or down until it reaches the level you want, right? If you know some coding, you might imagine it as just a simple conditional while loop. You keep increasing a value step by step until it reaches the desired value, and the loop stops. However, reality isn't that straightforward, nor is it always ideal. And to see what the real challenges are, we need to understand what elements actually make up a control process. Imagine you're driving your car on a long and flat highway. You want to keep your car at a safe speed, so you press down on the gas pedal to a level you think is reasonable, and then you just hold it there. Right now, the car is operating in what's called an open loop system. The input has already been set, in this case a fixed position of your foot on the gas pedal, and the output will be the car speed, which you assume will stay steady as you intend. Press less and you go slower, press more and you go faster. Simple as that. But in the real world, things are rarely that simple. Let's say a headwind picks up, a slope appears, or a curve forces you to slow down and then accelerate again. Suddenly, your speed isn't what you wanted anymore. You're still keeping your foot in the same position, but the car has slowed down or accelerated too quickly. This is the weakness of an open loop system. It doesn't have feedback. As soon as environmental disturbances appear, or the system itself changes, the output drifts away from the target with no way to correct itself. Let's return to the driving example. This time, you keep your eyes on the speedometer. The car slowed down, you press the pedal further. If it goes too fast, you ease off. Again and again, you make small adjustments to hold the speed close to your desired value. In this case, you are the living controller that keeps the car steady. Now, instead of only input and output, we're also using a new piece of information, the error. The error tells us how far the current value is from the desired value, or in other words, the difference between the current value and the set point. And our job is to drive that error down to 0. That's when we've reached our target. The error helps us create a feedback loop with which we know whether to speed up or slow down, to push harder or to ease off. Unlike the open loop system, this is now a closed loop system. You press the pedal, the car responds, you check the actual speed against the target, and you repeat the process continuously until you reach a comfortable cruising speed. But clearly, you can't just stare at the speedometer and adjust the pedal every few seconds for hours on it. You might get tired, distracted, or maybe you just don't want to hold your foot on the gas for that long. What you really need is a system that can do this for you more precisely, more reliably, and without ever getting tired. This is where automatic controllers come in. They made possible the invention of cruise control, which can keep your car at a steady speed. And to illustrate how PID works, this cruise control system will be the example we use throughout this video. Imagine you want your car to travel at a speed of 50 kilometers per hour, but right now the car isn't moving. So what do? Typically, you'd press the gas pedal hard to accelerate. As the car approaches 50, you'd ease off the pedal to avoid overshooting. It's human intuition exactly how the P controller, or proportional controller, works. Our output is calculated by multiplying the error by a proportional coefficient called Kp. Applying this to a car, we wanted to travel at 50 kilometers per hour, but right now we're at a standstill at 0 kilometers per hour. So the error is 50 minus 0 equals 50. Let's set the proportional coefficient Kp to 0.2 for example. So how much do we need to press the gas pedal? We simply take 50 multiplied by 0.2, which equals 10. So we press the gas pedal about 10 centimeters. After pressing the gas pedal, the car starts to accelerate, As speed gets closer to 50 kilometers per hour, the error will gradually decrease towards zero. At this point, we'll slowly ease off the gas pedal until we reach 50 kilometers per hour. This way, the car accelerates smoothly without overshooting the target speed. In this example, KP represents the aggressiveness of the system. The larger KP is, the more aggressively the system responds, and the faster the error approaches zero. To summarize, the P controller focuses on the current value. If you're not where you want to be, get there. In 1912, this is what another engineer named Sperry concluded after observing professional helmsmen turning their steering wheel to change direction. And for many simple machines, sometimes just the proportional term is enough. However, there's a major problem when we only use the P controller. Once again, we want our cars to travel at 50 kilometers per hour. We're gradually reaching that speed, but what happens when our car actually reaches 50 kilometers per hour? Now, since the error is zero, the output will also be zero. Then you'll take your foot off the pedal entirely and the engine will shut off. And because we're in the real world, friction will slow the car down below 50 kilometers per hour. Then the engine will turn back on as the error is no longer zero. However, at a certain fixed speed, the force created by the engine would exactly cancel out friction and the car would cease to accelerate, even though its speed hasn't reached 50 kilometers per hour. This is called the steady state error, and it exists in every control system when the target value is a number greater than zero, while our error approaches zero. Therefore, no matter where we set KP, if we set it too low, we'll never reach the desired value. If we set it too high, we'd have to constantly press and release the gas pedal, causing the car to jerk, meaning we'll never stabilize at the desired value. Our solution could be to add a constant to the equation so that the steady-state error matches the target value. But this falls short in highly dynamical systems like cars or super precise industrial machines. What we really need is an additional element that can track past errors and automatically adjust the current value to bring it back to the set point. And this is exactly what engineers like Nicholas Minorsky focused on while researching automatic shift steering systems in 1918. Like Sperry, Minorsky also understood how helmsmen measured proportional deviations by observing how they work at sea. But unlike Sperry, who saw it merely as intuition, Minorsky systematized the measurements and actions of those helmsmen. He wrote, "It has often been stated that the human intuition of the helmsman cannot be replaced by any mechanical contrivance, whatever its nature may be. Such a standpoint seems to be erroneous." And from that, he realized that to steer a ship, or just about any kind of automatic steering system, simply knowing the proportional deviation was enough. We need more advanced calculations to overcome the limitations of using only the proportional term. Looking back at the problem, we need a mechanism that adds up the remaining error over time. Even if each individual error is small, if it keeps lingering, the system needs to respond more strongly. And fortunately, we've already learned a familiar concept in math. That is the integral. By definition, an integral is the sum of the values under a graph over a unit of time, and it'll become a key part of the I controller, also known as the integral term. Our input is calculated by integrating the error from beginning up to the present moment and then multiplying it by an integral coefficient called Ki. However, it's clear that we can't calculate the integral the same way we find the bounded area of a function. In real life, we often don't even have an exact function to work with. So, to simplify things, we redefine the integral in our system as the sum of values taken at each fixed interval. For example, if the interval is 1 second, then every second we simply add up once. Let's set Ki to 0.012. Then what happens now? At the very first second, the error between the desired speed and the actual speed is 50 kilometers per hour. With the P controller, the gas pedal is pressed down 10 centimeters, proportional to that initial error. With a PI controller, in addition to the 10 centimeters for the P term, the control adds another 0.6 centimeters from the I term, calculated as 50 multiplied by 0.012. This way, the PI controller already introduces a small compensation right from the start. After a while, the air drops to about 33 km per hour. The P controller eases the pedal off to about 7 centimeters since the force is proportional to the error. Meanwhile, the PI controller has to accumulate error over the first 5 seconds, so on top of the 7 centimeters from P term, it adds nearly 2 centimeters from the I term. Step by step, the PI controller continues to increase pedal force thanks to the accumulated error, helping the car accelerate until it reaches its target of 50 km per hour. In contrast, with just a P controller, the car only reaches a little over 20 km per hour before stalling there. Once the car hits the correct speed, the error reduces to 0, the I term stops accumulating, but the pedal remains pressed at a steady level, enough to maintain speed and eliminate steady-state error. In summary, the integral controller focuses on past values. If time goes by and we still haven't reached the target speed, then speed up. So with the integral part, the system can gradually correct the small leftover errors over time. But because it works slowly, sometimes it's too slow. In situations where speed changes quickly, for example when the car suddenly goes downhill or faces strong wind, P and I cannot react fast enough. Imagine when the car descends and suddenly speeds up. The P part sees the air going down, so it reduces the gas. However, the I part can sometimes build up too much when the air drops too fast. At that moment, the speed overshoots and the system cannot respond in time. Even though the I part will then take negative values to cancel out the overshoot, but in some machines, you don't want that overshoot to happen at all. This is when you need a part that can look ahead, a mechanism that can predict what's about to happen, not just react to the present and the past. Let's look at the last case. Suppose you're driving and there's an obstacle ahead. Your task is to stop before hitting it. So how would you handle that? At this point, human intuition kicks in and you start thinking about how fast you're approaching this obstacle. If you're moving slowly, then there's nothing to worry about. You could just press the brake lightly and stop smoothly. But if you're going really fast, you'll have to hit the brakes hard and the car will stop very quickly. So clearly, even before you get close to the obstacle, you've already predicted the car's speed and reacted accordingly. And this is exactly how the D controller, or the derivative term, works. Recall your knowledge of derivatives. It tells the rate of change of the instantaneous slope at a point on the graph, or in other words, how quickly or slowly the graph is increasing over time. The faster the graph increases, the steeper the slope, and the derivative will also take on a greater value. Conversely, if the graph decreases, the slope is negative and the derivative will have a negative value. Our output is calculated by taking the derivative of the error at a certain point and multiplying it by a derivative coefficient called KD. Applying to this car, it's accelerating and the error is approaching 0. But you accidentally press the gas too hard and the car jumps from 0 to 45 km per hour in a very short time. At this point, the integral part hasn't caught up yet, and the next second it will overshoot past 50 km per hour. This is when the derivative part comes into play. Since the error is decreasing too quickly, the D term takes a negative value and subtracts from our output. That way, the car eases off the gas a bit to avoid going past the target speed. So to summarize, the derivative controller focuses on future values. If you're getting close to where you want to be, then slow down.
Okay, to help you better understand the PID controller, we carried out an experiment with a motor. And here's a chart that you can see. So, what is our task? Our task is to make this pointer align with the cable position as quickly and efficiently as possible. Now, what happens if we add only a P controller? Try to guess. It moves, but it doesn't quite reach the set point. It only gets to some angle and stops short. So, what if we crank up the P? Will it reach the target then? Maybe yes, but the thing is, it doesn't work that way. But the pointer will oscillate a lot. It will eventually reach the value. But the problem with oscillation remains, and we don't want that. Now let's try adding the I controller.
thì sao? Bây giờ mình sẽ thêm một điều y vào. Đó.
As you can see, the pointer stopped oscillating and reached the desired position. But the response is very slow, and of course, we don't want that either. So how do we fix it? Let's try to increase I.
Bây giờ mình tăng cái y lên. Đây.
There, it reaches the cable faster, but overshoot appears, meaning it goes beyond the target and then comes back. In system that requires stability, this is totally undesirable. Now let's add in the D term. It will help make the system more stable. And voila! There we have a perfect controller.
Thus, we now have an equation that responds to past errors, adjusts to the present, and can even predict the future. By fine-tuning the P, I, and D variables, we can control almost anything the way we want and at the speed we need. And the results achieved by these equations are no mean feat. To qualitatively assess the effectiveness of the PID controller, in 1923, Minorsky tested on the USS New Mexico. When installing just the P controller, the system adjusted the ship's heading with a steady-state error of 6 degrees. But after adding the I controller and increasing the P variable to an appropriate value, the system reduced the error from 6 degrees to 2 degrees, though this was still quite poor compared to the error of human helmsmen, and Minorsky couldn't reduce the error further by tuning only P and I. However, when the D controller was added, the system reduced the error to just 1/6 of a degree, a performance that surpassed most professional helmsmen. Moreover, when the ship was subjected to environmental disturbances, the PID controller produced, quote, the remarkable result that such a disturbance has no influence upon the performance of the device. So what did Minorsky do after inventing a near-perfect controller capable of automatically managing a system over long periods with accuracy surpassing even humans? He was ignored. Minorsky's PID system was removed from the US New Mexico, and he was not permitted to test an automatic system on any ship again. Captain H.S. Howard of the U.S. Navy explained, the operating personnel at sea were very definitely and strenuously opposed to automatic steering, and they wished us to have nothing further to do with it after these tests were completed. Even Minorsky's thorough and brilliant research paper received little attention at the time, and ultimately, in 1930, he had to sell the patent for his controller to the Bendix Corporation. However, even when engineers were aware of Minorsky's work, they lacked the devices and sensors capable of converting weak measurement signals into feedback components with sufficient power to operate a complex system. Nicholas Minorsky might have been forgotten if not for the collaboration with another equally significant figure in the development of automatic controllers, that is, Elmer Sperry. Sperry's engineering company, the Sperry Company, conducted further research into automatic control systems, but they all lacked a clear and foundational theoretical framework. These controllers often combine components in complex ways, making them difficult to develop further in the future. In 1937, Nicholas Minorsky analyzed Sperry's controller in The Engineer magazine. In it, he provided clear theories and systematized the components used in an automatic shift steering system, thereby helping both Sperry and future engineers to establish a foundation for developing commercial automatic systems. Moreover, Minorsky's work also inspired Harold Hazen and encouraged him to study servo systems, which in turn became an important reference for new control engineers. We could say that without Minorsky's pioneering work on complex dynamic systems, automation might not have developed to what it is today. Indeed, once the PID equation was integrated into electronic devices and modern microprocessors, the potential of this three-part system became limitless. It's been used to control almost everything, from ovens, air conditioners, and navigation systems to factory machines, robots, spectrometers, and much more. PID has become so good at controlling everything that sometimes we forget the simplicity and elegance of an effective controller. Elmer Sperry once said, "Necessity is the mother of invention," so the reverse would also seem to be true. Each development in science and engineering necessitating the development of some device or devices to increase the efficiency of the prime development. Indeed, had we stuck with the all centrifugal control systems, or had we assumed that control could only rely on human intuition, or had we not attempted to analyze complex systems, we might never have realized how challenging yet beautiful it can be to convert one value to another. And that's the very purpose of scientific research. Measuring or calculating the obvious things around us might seem unnecessary, but only by deeply understanding how everything works can we gain the power to control the world as we wish. For this, we owe much to Nicholas Minorsky, or as recalled Irmgard Flugelot, his colleague at Stanford University, the tall, slender man presenting the grand senior type when he was walking with his characteristically bent soft felt hat over the Stanford campus, perfectly absorbed in scientific ideas.
Ok, rồi. Xong như vậy. Đi về, đi chơi. Bật lên, bật lên. Ồ. Wow. Bật lên.